let us look at the tangent plane to a surface. We're also going to be looking at the normal vector to the surface, and of course the normal line would be parallel to that normal vector. We're going to use the help of this document. It's called the tangent plane to a surface by Bruce Ikenaga. That's what I would pronounce his name. Alright? Now, here, the surface and the curve. Here you can see a surface. Let me just copy it and paste it over to our whiteboard. So, here, we have a curve. And see the curved surface here. Alright? So this is our surface. Now, the plane. You know, a plane is some type of flat surface. It could be the tabletop, a tile, the floor. This is a plane, right? And it's tangent to the surface. Tangential to the surface, meaning it's touching the surface at one point. It doesn't cut through the surface, right? It just touches it at one point. Alright, so that's what we have. We have our surface and our tangent plane. Now, suppose we consider that we have our surface being a graph of, in this case, z is equal to a function of x and y. That's our surface in 3 dimensions. Alright? Then we have a specific point, some point where, well, we call it point of tangency. It's where our plane touches the surface, the curved surface. So the coordinates of that are A and B. Now, here, what do we call the third point? This is in the form x, y, z, you know. But we're going to specify exactly some number where the curve touches the surface. It could be, for example, suppose z is equal to x plus y. And we have 2 for x and we have 5 for z. Well, z would be 2 plus 5. In this case, z would be 7. Alright? If we specify these points. So, our 2 would be A. Our 5 would be B, and then our Z would be A plus B, alright? But it may not be A plus B, it could be something else. So Z in this case is f of A, B. Some function of A and B put together, alright? So we have our point. Our point is at A, B, f of A and B. Now, suppose you zoom in to this curve and you consider a piece of that surface. The more you zoom in, the smaller the piece of the surface is. It will be curved, but as you get nearer and nearer to it, it would get flatter and flatter. Alright? Now let's go back to our document, and I'm going to put a link in the description of this video to this document, so you can check it out there and download the document. let's paste our piece of surface here. Nice. Let's look at this. This is a piece of our surface. Now, we have our change in X and our change in Y. Here, we have our graph. Alright. Let's say this is our graph. X, Y, and Z is going up. I put the part that are negative, that's below 0, as dashed lines. Here, watch. This is our X, this is our Y, this is our Z. Alright? These are the various coordinates, the X coordinate, Y coordinate, Z coordinate. Some people say Z coordinate, I just say Z coordinate. Alright? Now, suppose you have a change in Z, in X. That means you're sliding along this line X. Alright? You're sliding along X. Now, you're considering the change in Y and the change in Z as well. When you slide along X, in order for Y to change, you'd have to shift either to the left or right of where you're sliding, alright? But there's no shifting of Y. So there's no Y component. There's no Y component in the change. There is, they have dz, dx here. But I'll use del x to show a small change in x. You're changing x. So, looking at the coordinates, alright, you're looking at this vector. As you change x, you're going along this vector. Vector A would result, the changes that would result in A would be a change in x because you're sliding along x. Y is 90 degrees to x. It swings left and right, and the left and the right of x. But there is no change in y. So you have comma 0, comma. Now how is it changing? Let us see. When you slide along this vector, right, x is changing, but notice you have a delta z by delta x times the change in x. Because guess what? If you should slide, let's say we have our delta x here. Now, this is our delta z. Alright? Now, how do we get that our vector? Or let's look at the slope of this line, which would be tan of this angle. The slope would be rise over run, which is delta z by delta x. That's where this delta z by delta x come in. Now, here, if we move delta x and stop at this point, we would achieve this height in terms of delta z, alright? In order to achieve this height, we'd have to move all the way out here. So, the change in z depends on the change in x. So we have to multiply by delta x. But suppose we had a steeper curve, somewhat like this. Alright? Then we would not have to wait until we reach all the way out here to achieve that height. We would get the height from the same height. Oh, from just moving here. So it also depends on this the steepness, delta z by delta x. So in this case, we multiply delta z by delta x times the x. In other words, this goes back to our argument in a previous video. We were saying, for example, the amount of money that you make depends on the change in money per change in day multiplied by the number of days that you collect that money. $1,000 a day for 5 days is $5,000. $2,000 a day for the same 5 days, $10,000. Or $1,000 a day for 10 days is I say $2,000 a day for 5 days, $10,000. But $1,000 a day for 10 days is the same $10,000. So you see what I'm saying? You have delta z by delta x times the change in x dx. So that's where this comes in. Alright, so here, this change in z is delta z by delta x times, times the change in x. So that's a vector there. Now, a similar argument would hold when it comes to the vector b. Alright? We're moving in this direction. As we move in this direction, right? Similar to this. The change that produces this change in the vector b would be what? As we move and change y, dy, you notice that there is no change in x, going straight along y. You're not moving to the left nor right of x. You're just going straight. So there is no change in the x component. Of course, the change in y is del y, and we also have the change in z caused by the change in y. It would be delta z by delta y times the change in y, del y. Alright, so let's just get rid of some of these workings here that we had before. And this part. Alright, so now we consider that the vectors A and the vector B, consider them as being flat. Alright? Now A would be B would be that vector. A would be that vector. So this is B, this is A. On the surface, remember, we're looking at a flat surface somewhere here. Let me draw it with straight lines. Our surface is like the sheet of paper, right? We have a flat surface. And then our A is lined up properly, but the B, I'm going to need to make an adjustment to the B. the B line. Alright, good. Those are on our surface, but the thing is, we need the normal vector. So how do we do that? Now, if you remember, when you were studying vectors and we look at the dot product and the cross product, what was the cross product again? Well, the cross product of two vectors. It was a third vector that is at 90 degrees to each of those vectors. So this vector would be our cross product if we consider it being 90 degrees to A. It's perpendicular to A and also perpendicular to B. Alright? So we need to find the cross product of these two vectors, A and B. Vector A and vector B. Alright? Now, here, how did we find the cross product again? Well, A cross B was a certain determinant. It was of I, J, K, where I, J, and K would represent the directions like X, Y, and Z. Alright? I, J, and K would be the directions. Then the components of A would be delta X, 0, then del X, 0, or the change in X, 0, then delta Z by delta X times change in X. Alright? And then the components of B would be 0, delta Y, del Y, then delta Z by delta Y, del Y. Remember, I call this shape delta, this shape delta, and this del. Del mean a small change in delta in the derivative of. Alright? So remember those things. So here it is 0, change in Y, rate at which Z changes with respect to Y by a change in Y, or the derivative of Z with respect to Y by a change in Y. Alright? Now, let us find the cross product here. This is equal to, remember, you have I multiplied by, you're going to eliminate the rows and column with I. So you're going to find the determinant 0, delta Z by delta X del X, then del Y, delta Z by delta Y del Y, minus, here it would be J minus J times, then you eliminate the rows and column with J, and what you're going to have are del X, change in X, delta Z by delta X, change in X, alright, times 0, and you have delta Z by delta Y, change in Y. See that? Plus what now? Going to be plus K, and the determinant you multiply K by is, you eliminate the row, you ignore the rows and column with K, so you multiply by change in X, 0, 0, change in Y. So it's changing x, 0, 0, changing y. Okay, so you see that from out here. So let's look at it now. It's I times going to be this times this, right? 0 by this minus this by this. 0 times this is 0, so it's 0 minus going to be delta z by delta x, changing x, changing y, minus j times going to be delta z by delta y, changing x, changing y, so you multiply this by this, minus this by 0, which is 0, alright, plus k times, alright, this by this, which is delta x, delta y, minus 0 by 0, which is 0. Okay, so this is equal to negative I delta z by delta x time changing x, changing y, minus j delta z by delta y, changing x, changing y, plus k delta x, changing x, changing y. Alright? So, you see that. Now, here, this is A cross B, so let me just repeat the A cross B here. Now it is equal to, if we factor out the change in x, change in y, we're going to have change in x, change in y, and note that the I, j, and k are really directions. Let's ignore those directions. What we're going to have is delta z by delta x, right? The negative, don't forget the negative sign, and the minus delta z by delta y, and then here plus 1. Right? Now, this is the normal vector. Alright? If we look back at our document here, so we got that. It's a normal vector. So this is all then referred to as a normal vector to the surface. And it's denoted by an N with the arrow above it. Then it says the tangent plane is this. In a different video we'll come to how they get this to be the tangent plane. Alright? So here, what it's saying is that the normal vector is equal to negative delta z by delta x minus delta z by delta y plus 1. Alright? Now, remember, you still have your I, your j, and your k here to show the directions that, and that this thing is indeed a vector. Alright? Now, they say that a tangent plane, this is a normal vector. Let me just make a note. This is a normal vector. Now the tangent plane is, they said, minus delta z by delta x times x minus a. Remember. Alright, so we'll come to that later. Minus delta z by delta y y minus b plus you have z minus what? F of a b, right? And that is equal to 0. That's how it's sometimes written. Now the x minus a, remember it's a change or a shift, alright, in a. So remember your graph, you have your x and y axis, and you have, for example, y equal x will look like this, but y equal x minus 1 squared. Oh no, y equal x squared wouldn't look like that. It would be more like this, right? Y equal x minus 1 squared. That's x minus 1 all squared would look more like this, where this is above the 1. So the x minus a is a shift, and you need to shift y as well. So x minus 1 r squared, and then you, if you say minus 2, it would come down here and go beside negative 2, alright? And then you shift your z. But all when you plot the plane, it will be in 3 dimensions, alright? So this is the normal plane. Alright, and these x and y's would constantly be changing. They are variables, and whatever it changes to, you plot each of those, so you get your plane, alright, shaded plane for each point. Now you could multiply both sides by negative 1. Alright? If you multiply both sides by negative 1, you get delta z by delta x, x minus a, plus delta z by delta y, y minus b, minus z plus f of a b equals 0. That's what you would get if you multiply both sides by negative 1. Alright? Now, suppose you add z to both sides. What would happen? This would go, and you'll have equal z. Rewriting it like this. So z would be equal to delta z by delta x, x minus a, plus delta z by delta y, y minus b, plus f of a b. So that's how you sometimes see the equation of the tangent plane written. Alright? This is how they get it. Now, another thing I want to consider. Let me just, before we do that, let me just put all of this in one and make a copy of it. Suppose you consider this, alright? And let us say you consider the, let's say y does not change. So this part becomes 0. 0 times this part is 0. So this goes. Suppose you consider that happening. Then when you transpose for this, the delta z by delta x becomes equal to, if you should subtract f of ab from both sides, what would happen? You'd have z minus f of ab divided by x minus a. You see that? So rewriting it, delta z by delta x. We run out of scrolling space, so we can't scroll anymore. So you have to go to the side. Because z minus f of a comma b over x minus a. Notice the change in z, what this is saying, the change in z is equal to rise z minus f of ab is also a z, you know, but it's another z. This is the change in z over change in x. A is a specific point in x. So x minus a shows a change in x. So you see the delta z over delta x. Z minus another z over x minus another a. So it is change in z over change in a. I mean change in z over change in x. See that? Now suppose we consider that. So back at this. Suppose we consider that there is no change in x, and we're looking at change in y alone. Then this part becomes 0. 0 times 0 is 0, so this part will disappear. Now we transpose and make delta z by delta y the subject of the formula. You would get z minus f of a b, which is a change in z, divided by the y minus b. So here you can see we have a delta z by delta y, change in z over change in y, z minus, this is another z, this is a z, a specified z, z minus z, change in z over, what happened to the b? Oh, over y minus b, which is a change in y, alright? So you see that part there. Let's erase this. So this here, you have this formula at the various places all over the internet. If you look for, if you search for the formula for the tangent plane to a surface, you see this formula or something looking like it. Alright, so that's it for now. I will see you in the next